My name is Wang from Intel Open Source Technology Center, and I'm based in Shanghai. So like Toronto, Shanghai is a big city, and it's advanced in many areas. But there is one thing I want to complain about Shanghai. It's not the crazy house price today there, but the bad traffic, especially in the morning or weekdays, cars, buses, and trucks from different corners centralized on the main road, which gives rise to a bumper-to-bumper traffic. The throughput and latency of such a centralized traffic are horribly bad. Like some of my coworkers even spend like 4 hours per day on the road. It's incredible, right? So what is interesting here is that we find a similar problem with today's network traffic between VMs. So that's basically the reason I'm presenting this vhost PCI design. So in the design, a vhost PCI device is a new volatile device, and it enables a point-to-pointer inter-VM communication, which eliminates such a centralized traffic. So let's first have a look at the agenda of today's presentation. So part one is about the usage and the motivation. Network function virtualization, NFV, is a use case which relies on a high-performance inter-VM communication scheme. So in this part, I will introduce why the existing solution is not suitable for NFV case, and how vhost PCI improves it, and I will show some results of our POC work. And in part two, I will introduce the details of the design. This is actually the theme of this presentation. So in part three, I will summarize the current status of our work. So starting from part one, let's first have a look at what NFV is, just in case some of you may be not familiar with this concept. So basically, NFV is about the transformation of network appliances. So a network appliance today is a network function implemented using hardware. So what the people want is to transform each of those hardware-based network function to software-implemented virtual network function, VNF. A VNF basically runs on a VM. So this transformation relies on a high-performance inter-VM communication scheme. So here I got a figure from ETSI, from the architectural framework made by ETSI. So what this figure illustrates is a VNF forwarding graph. So to be more precise, the packets first reach VNF1, and then after some processing, they are forwarded to VNF2A, and then they are either forwarded to VNF2B or 2C. And finally, they reach VNF3. Those VMs work together to provide a service. So here, it actually has two data flows. And those two data flows generate very frequent inter-VM communication. So here I show you how we can use vhost PCI to set up this two data flow. So here, VNF1 is equipped with a vhost PCI device, and it communicates directly to the virtio-net device of VNF2A, so the packets go like this. And in VNF2A, it has two vhost PCI devices. So the packets can be directly forwarded to either this virtio-net one or go to this virtio-net. And then finally, the packets are forwarded to VNF3. So here we have the two data flows here set up. Now I think it's time to introduce why the existing solution is not suitable for such frequent inter-VM communication. So here in this example, we have 4 VMs connecting to one central vSwitch. So each VM is equipped with a legacy virtio-net device. And this virtio-net device is backed by a traditional vhost-user backend implemented in the vSwitch driver, such as DPDK. The code path of transmitting a packet is long here because the packet has to reach the central vSwitch first, and then the central vSwitch driver copies the packet to its destination. So the implementation is a little different, but if we animate the process that all the VMs transmit packets to their destination, it will be like this. So here a bumper-to-bumper traffic shows up in the central vSwitch, and those packets need to be copied to their destination one by one. So this is actually not scalable because if we have more VMs connecting to this central vSwitch, so here become a bottleneck, and the throughput will drop significantly. I will show you the results in later slides. So here it shows how this is improved by the vhost PCI device. So you see the central vSwitch now is distributed to each VM. Since this presentation mainly focuses on the vhost PCI design, which is about the transport layer design. So here I'm not going to talk about the switching technologies here. The key point here is that each VM is equipped with a vhost PCI device. And this device enables a direct copy of packets from the source to the destination. So if we animate the same process here, all the packets are transferred to their destination at once. So this one has better scalability. So we've basically done a POC work to compare the two solutions. And we used a benchmarking method from OPF called vhost-perf. And I've posted all the testing environment here, but I'm not going into details. The key point here is that we wanted to chain 2 to 5 VMs. So in the traditional way, we chain the 5 VMs through this central vSwitch, and the packets go to the central vSwitch, which directs the packets to the second VM, and so on. The packets go all the way down to the 5th VM. So in the vhost PCI device, it's chained like in this way. So the packets go to vhost PCI device, which directly parse the packet to VM2. And finally, the packets are transferred to the last VM, VM5. So here we can see the results. In the vhost user case, when we have 4 VMs chained together, the throughput drops significantly. It's almost like 42% here. So, but in the vhost PCI case, there's no such significant performance drop here. Okay, here comes to the most exciting part, the design details. So by far, I've talked a lot about vhost PCI for networking usages, but I wanted to mention here is that this design is not limited to networking usages. We basically wanted to enable vhost PCI to support all the front-end volatile devices like volatile SCSI, volatile console, volatile block, and so on. So let's start from a high-level overview of this vhost PCI design. So here we have one QEMU gets booted. And what's special here is that this QEMU creates a vhost PCI server. And this server is implemented using QEMU socket. So it's a socket server. And this server manages vhost PCI devices like device creation, hot block, and destruction. Here we have a second QEMU gets booted. What's special here is this QEMU creates a front-end volatile LED device, and the front-end and the LED device is associated with a client socket, which is also implemented using QEMU socket. So this client socket connects to the server, and they communicate to each other via vhost PCI protocol. Then the server creates a new vhost PCI device and hot blocks this device to the VM and initialize the vhost PCI driver. So here we have a second QEMU gets booted. So the difference here is that this QEMU creates 3 volatile devices of different device types, like the virtual SCSI, net, block, and each of those front-end devices creates a client, and all the clients connect to the server, and they talk to the server via the vhost PCI protocol as well. So what the server does is to create a new vhost PCI device 2, and hot plugs this device to the VM and initialize the related driver. So we can see from this figure that the vhost PCI server creates a vhost PCI device for each VM. And all the front-end devices from the same VM will share the same vhost PCI device. So I've picked out all those components which are new to the current QEMU, and I will talk them one by one in the later slides. And the remaining parts, like the virtio-net driver and all these virtual drivers, will remain unchanged. So let's start from vhost PCI server, which plays a key role in the whole design. So to use a vhost PCI-based inter-VM communication, so a VM's QEMU needs to create a vhost PCI server using these commands. So the red ones here are the new commands I'm going to patch the current QEMU, like the connections here, which specifies how many clients can connect to this server. So in current QEMU implementation, it only supports one server to be connected by one client only. So here I wanted to add the support to make it like one server to be connected by multiple clients. Next is the vhost PCI client. So to use a vhost PCI device on another VM as a backend, so the originating virtual device, that is the front end, should supply a vhost PCI client and connects to the front-end server. So here are the command example to create this client. This one is due here. And the client communicates to the server via the vhost PCI protocol to set up the inter-VM communication channel. So here is something about the vhost PCI protocol. So basically, this protocol consists of two message types. One is the socket message, which is used between the client socket and the server socket. And another one is the control queue message. This one is used between the vhost PCI device and the vhost PCI driver. So whenever the client transmits a message to the server, it will send packets from the device to the driver. So it's sent through this control queue. Regarding the protocol message, I've listed the main contents here. The first one is vhost PCI get UUID. So UUID is used to identify a front-end VM. Like in the previous case, a VM creates 3 front-end devices. When they communicate to the server, the UUID will remain the same. And the second one is memory info. This memory info is basically transferred by the client to the server. Then the device uses this memory info to map the entire memory of the front-end VM so that the vhost PCI driver can access any memory that belongs to the front end. The third one is about the device info. It's also transmitted by the client to the server. So this info includes things like a device type, which specifies if this is a virtio-net front end or virtual block, virtual console, and so on. And it also contains vRing address so that the front end can copy the packets to the correct place while accessing the vRing. And the last one is the feature bits. Like all the front-end virtual devices have feature bits, and they need to be transmitted they need to be negotiated with the backend vhost PCI device so that the vhost PCI driver can behave correctly when it copies packets to the front end. So here shows how a vhost PCI device is created. So first, the server creates a PCI device instance, which is like the device structural allocation, initialization things. And then it sets up the memory basically the QEMU maps the memory from the front end, and according to the size of the front end, it will reserve like a double size of the memory size it received from the front end. For example, the front end size is n, then the whole memory region size will be 2n. So the remaining part is reserved for memory hot block. And then this memory region is registered to the VM via a bar. And finally, the device is hot blocked to the VM. Okay, here comes to the vhost PCI driver. So you may be curious about how a single vhost PCI can support so many kinds of front-end devices. The secret is here. So the driver contains multiple functionalities, just like a transformer that you saw in a science fiction movie, which has lots of functionalities. So here we have all the backend functionalities contained in single vhost PCI driver. Like the vhost PCI LED corresponds to the front-end virtual LED. The vhost PCI SCSI corresponds to the front-end virtual SCSI, and so on. So if we think more about it, it's actually more sophisticated than a transformer that you saw in the movie. Because as far as I see, a transformer can only transform to use one of its functionalities at a time. But here, all the backend functionalities can function at the same time, as long as this VM has enough CPU resources. So to be more precise, the net functionality, SCSI functionality, and block functionality can copy packets to the front-end devices at the same time. If we look into the code a little bit, so we will have an array of vhost PCI device, and this structure includes the 3 fields. Like the first one specifies the type, it's LED, SCSI, block, and so on. And the device ID is used to identify the device. For example, if the front-end device is a LED device, then this device ID can be used to store the MAC address. And finally, it's a pointer to the device-specific structure. If it's a LED device, it will point to a LED dev structure. And in the initialization code, it will create a LED dev to the kernel so that the kernel network stack can know there is a new LED dev device so that it can use it to transmit the packets. So here, I'm going to talk about how the backend functionality is designed. So I will use the vhost PCI LED as an example here. So in this example, the front-end driver, virtual LED driver, has a pair of V rings, a TX ring and an RX ring. So this is used to transmit and receive packets. And what we are doing in the backend functionality here is to mirror it. When I say mirror it, I mean we share the V ring to the backend, and then we crisscross the V rings. So like the RX ring in the front end will be the TX ring in the back end, and the TX ring in the front end will be the RX ring in the back end. And this backend functionality is responsible for copying packets in and out of the originating device rings. So here is the last part. I will summarize the current status of our work. So currently, everything is going well, and we've done initial POC work, and the results have been shared. And I've also sent out the design RFC v2 to QEMU and KVM mailing list. And in the meantime, I've started to implement this RFC v2 design. Okay, here comes to the end of this presentation. Thank you. Do you have any questions?
I would like to understand what is different from existing vhost-user in terms of abilities, since vhost user also can enable to backend and another QMO, and another QM can serve theoretically as a backend, and also to give the access to the another guest memory. So what specific abilities vhost PCI gives comparing to vhost user?
I think for the legacy vhost user, so the packet has to go to the central vhost switch first, like a OVS or...
I'm talking about in terms of protocol, since vhost user has not to be connected to a central party, but be directly connected to another QMO if it implements functionality of backend.
I have the same question. Right? Can you go back to your performance slide?
Yeah, sure.
Right. So have you tried possibly using 4 different vSwitches there and just connect pairs of VMs to 4 different vSwitches? And then you would just basically get more threads to do packet processing, and then data path will look exactly like what's on the right.
Well, if we split this switch to 4 switches,
right,
then we need to assign more resources to the switches, right?
The switches don't have to pull, right?
No, as far as I see, the switch driver is like a DPDK. It's using the polling driver. And
that's only if you need to pull hardware, right? If there's no hardware, if it's just a vSwitch, then you can just wait for kicks and throw interrupts, right?
I think at least we need to...
I mean, you should probably do that experiment and see, if you actually do get the performance gains.
I mean, it will have more resource consumption here.
Yeah, you can disable the polling, right? Disable the polling and then try it out. You don't have to busy poll.
Then this will increase latency as well, right?
But I mean, you have to do something on the other side as well, right? I mean, you have to have something that's waiting for the even FD to kick and stuff like that, right? I mean, it seems to me the difference between these 2 pictures is how many threads that can process these data paths in parallel. That's really the difference, right?
Yeah. But another thing is if we have a central switch here, the latency is also longer. The package has to be sent to the central switch. It will be 2 copies, at least 2 copies.
Are you using OVS DPDK?
Yeah.
Then there is a vhost user implementation inside the vSwitch, right? And that's blocking the ring.
Yeah, I think...
that shouldn't give you extra latency. I mean, you possibly try a vhost bridge, without any of the OVS logic in there. Try that.
Yeah. I mean, so if we use the vSwitch, the packet will first be copied to the M buffer of DPDK if you see the implementation.
Okay.
And then the DPDK driver will copy the packets from the intermediate M buffer to the destination. It will at least be...
But that's something you can optimize. I mean, if you write a vSwitch that all it does is switch packet between 2 VMs, you can optimize that. Right. Try out the vhost bridge.
Okay. Yeah. It will be 2 copies.
You can copy directly from one ring's TX to other ring's RX, right? Right. No, you don't have to use the VK. Just use the vhost protocol.
Yeah, my question is kind of similar with the previous 2. Yes, I think if we use a switch with 2 vhost user ports and connect the 2 VMs, I think it's one copyright. But I'm not quite sure. Okay, I'm asking other questions. And firstly, you say that the PCI devices are hot plugged, right, when the connecting is happening. And I want to know, so because PCI is very complex strategy, and you just plug into somewhere you like, or so the first question. And the second question is, I want to know, basically this is to solve something related to memory sharing, right? Yeah. To share memories between VMs, and I'm still not quite familiar with existing methods to share memory, something like share SHMEM, I don't know. But could you explain more about the difference between the methods. Thank you.
Okay, regarding your first question, you are talking about the hot plug of the PCI device, right? I think it should be.
Oh, sorry, I stay there. I mean vHost PCI device when there is a connect and you will create a device and hot plug into the VM, right?
Yeah.
Yeah, I mean that device. It should be attached to something like a PCI bridge or root, right?
Yeah.
So where will be attached? For example, if I have two bridges, two PCI bus, and where should I attach it?
I think the current virtual device also can hot plug. We can also hot plug other virtual devices to the VM, right?
Right.
It will be the same, I think.
I haven't played a lot on the hot plug, but I think we need to specify. Do we need to specify? For example, I want to plug a PCI, virtio-net PCI device under a specific bus, and yes, right. So you are automatically attaching something. So maybe it's not a very important question. I'm just curious about it. Maybe you can move on to the next, if you like, about the difference on different methods to share memory between VMs. Do you have any research on existing projects or methodologies that can achieve the same goal?
No, regarding the memory sharing, so it's like the vHost user, which transforms this memory info, like this address, user space address, something like that. So the current vHost user, protocol supports this memory information transferred from the front end to the back end in the vSwitch. So we will transform the same information from the front end to the back end. And we set up it using the QEMU memory region. Is that clear?
My question is actually about the old ways to share memory between the VMs. And if you want to talk more about the vHost user case, it would be okay as well, because that's always my question. I think there is only one copy. So OVS should only copy data from VME, from a VME reading to the VMI reading, from vHost port 1 to vHost port 2, only one copy. That's what I thought, but I'm not sure about that.
No, I think that one is two copies. So first, it will copy packets from the source buffer to the intermediate buffer in the vSwitch, okay, like allocated by DPDK.
Yeah. Okay. So that's
so it's like in and out. For like out and in. For out, it will have one copy, and for in, it will have another copy.
Okay. So, I'm not familiar with OVS, but why not we just maybe there's some reason maybe. So okay. Thank you.
What happens when your VM that is running your vHost PCI device, what if that crashes? So if you go back like one slide, for example, what happens when VM2 crashes?
VM2 crashes?
Yeah, so VM2 contains all the state that basically the basically contains all the state of that PCI device, doesn't it? Yeah. Can you resume? Can you somehow send the other host? Sorry, I got like a machine check, the PCI error, AER, whatever, to reinitialize the device. Or the nice thing about normal network connections is that everything's self-contained. I'm not sure how vHost user deals with that, to be honest. But in that scenario, you suddenly put your device emulation into a different VM, which then again can crash separately from your normal operation.
Yeah, here if the VM2 crashes,
yeah.
So do you mean that the chain will be broke or?
Right, the chain is broken and that virtio-net device there is dangling and trying to talk to somebody.
This is even the same with the legacy case, like I can show it. So here, if this VM quits, then the packets cannot be sent to VM3, right?
So in that case, if the vSwitch crashes, I don't know what happens, to be honest. If the other VM crashes, it just restarts, and you can talk to the other VM again.
Yeah, so in this case, if the vSwitch crashes, then basically the packets cannot be sent between VMs.
Okay. I'm not going to go into the implementation details of whether Open vSwitch is good or not, or whether like vhost user solves all the issues today. But in your case, you basically, so Open vSwitch is like this one piece that you basically have to guarantee doesn't crash ever, whereas your VM is like one more attack surface, one more whatever. It could even be just killed by the OEM killer and you don't realize it. It's just more complexity on that layer, which means you really need to take into account the case that that VM just goes down and restart whatever was happening before. You probably want to have the same on Open vSwitch if it doesn't do it today. I don't know. I haven't looked into it.
I think the departing point of this design is that we enable a point-to-point inter-VM communication. If we say we have two guys communicate to each other and one guy has gone, so there is no communication actually.
There should be every piece in. Okay. In your traditional VM model, if your QEMU instance crashes, your driver crashes, everything is gone, period. The VM is just down. You restart the VM, everything's good, everybody's happy again, because you just connect your VM to whatever you have from the networking side. In that case, you can suddenly have you splitting off your device model into different processes, in which case you basically have to make sure that they either all go down together or you just are able to restart individual pieces. And I think restarting individual pieces is probably smarter because you get more uptime.
Okay, I get your point. So here, if let me check. If VM2 gets down and we reboot this system, like how do you
If
say?
VM2, if the upper right goes down and it goes back, you restart and it goes back up, it can still talk to the upper left, but it can no longer talk to the lower right.
Yeah.
And that's the problem you probably want to solve before you consider this production usable.
So one solution to this one, I think, is we can let the client send a periodic message to this server. And
you can just have the server send a message saying, "Hi, here I am. I'm now initialized." And if the client was connected to something beforehand, it like submits a PCI, whatever reset, an AER message, anything that basically tells the guest that device just broke, and you have to reinitialize something. Either way, we don't have to go to details, but it's something you probably want to consider.
Okay, thank you.
I just remember around a year back, I was implementing this solution where I was comparing the performance for vhost user against the vhost kernel. And I did implement this solution where we have a VM which transmits a packet to a vhost user and it reaches to another VM. So I have the source, and in that case, there was no vSwitch involved. So, and for memory sharing also, we can use shared SHMEM, or we can directly mmap memory. And there was no vSwitch involved in that communication. So that was the first point I want to make. And the second one, in the vSwitch, apart from just you told about bumper-to-bumper traffic, it makes many more important decisions about routing, etc. So how those will be made in your architecture. And third thing, you talked about PCI net, PCI bulk back, and control rings. So how these control rings will be handled for, will there be a separate control ring for PCI net, PCI bulk, or are you trying to combine those rings? So yeah, I have a working solution where this vSwitch is not used, and
Yeah. So I didn't get the point of your first question.
yeah,
Can you repeat
so
again?
that's what I want to say, that vSwitch is not used. I have a solution where this packet goes from VM to vhost user and again to VM without any involvement of vSwitch.
Oh, you mean the switch inside of the VM?
Sorry?
Do you mean the switch inside of the VM, like this figure?
Yeah, standard VM. Yes.
You mean this one is not necessary to be here?
No. If you go to the initial slide, in the present architecture, you said that vSwitch is involved and traffic from all the VMs will come to vSwitch. What I am saying is that, as he mentioned, vSwitch doesn't come into picture.
So it's 3:10. If anybody wants to leave for the break, feel free to do that. others might either discuss it now during the break, or even better, during the BOF session. There's already a session about vhost PCI that, and in general NFV that we wrote on the easel, so sorry.
No problem, it's okay. So yeah, maybe I will comment it on the patches that you have posted, but yeah.
Yeah, sure.
Yeah.